Good day and a very warm welcome on behalf of NTI Audio. Thank you for joining us for today's webinar. In this webinar, we are talking about advanced topics of GlideSweep analysis. This is actually a follow-up presentation of our last webinar, which was dealing with the basics of different sweep analysis methods. But today we are focusing on GlideSweep analysis. Let me please introduce myself. My name is Markus Becker and I'm assisted today by our product manager Greg Schmiedle. He will take care of the incoming questions during the presentation and afterwards. The contents that we have prepared for you start with a brief look on the fundamental principle of GlideSweep analysis. Afterwards, we will say some words and hints about test parameters, how to set them, the optimum ranges and so on. We will cover the aspects of acoustic testing, and we will also spend some hints on the testing of electronic devices. We have also prepared a practical presentation for you, and after that we will summarize the key information that have been included in this presentation. Let us first take a brief look on the fundamental analysis method of glide sweeps. Maybe you remember the step sweep analysis where we had a stepwise increasing or decreasing frequency over time, and the measurements that we selected, the active measurements, being executed for each of these steps. GlideSweep analysis follows a completely different approach, and I want to show you that. Here we have a schematic sketch of a GlideSweep transmission, which means we generate the GlideSweep, we transmit it through the device under test, and we receive the output of that device. Now in a second step, we would calculate by means of FFT the spectra of the generated, the emitted GlideSweep signal and the incoming, the received GlideSweep. Here you see the emitted spectrum and here you see the spectrum of the received signal. Now in the next step, we apply a so-called deconvolution. That is a complex mathematical procedure. We could also say it's a division of spectra, or which is mathematically not absolutely correct, but maybe better to imagine, we could call it a cross-correlation of these two spectra. And this deconvolution of the two spectra before and after the device under test gives us the impulse response, or we could also say the transfer function. And this impulse response now is the base to a wide number of different results. First, we have the standard results like level, phase, distortion, and so on. But, and that makes the beauty of GlideSweep analysis, we also receive more advanced information like the runtime or latency, or the reverberation time of the transmitted signal. So here you can see that with this method, which is completely different to a step sweep analysis, so with the GlideSweep analysis, we can get a huge number of different results out of a single fast and short signal transmission. Now, when we set up a GlideSweep test, we have to decide how to adjust a couple of parameters. And one of them is the start and the stop frequency, or the bandwidth we are covering with our GlideSweep. Now this depends, of course, strongly of the device under test and of the environment and the test specifications. But basically, as a rule of thumb, we recommend definitely to consider the performance or the specifications of the device under test. And especially when we talk about loudspeakers that need to be tested, take care that the GlideSweep bandwidth also covers the resonance frequency or frequencies of the tested loudspeaker. And I want to show you that in an example. Here we see the frequency response of a woofer, we start at 50 Hertz and we go up to 2 kilohertz. But if we look at the impedance response, we see that this bandwidth here hardly covers the resonance frequency of the woofer. Now, because we want to know this resonance frequency more accurately, we want to have a clearer picture of this peak, it is strongly recommended to extend the bandwidth. And that's what you see here. We start at 20 Hertz, go up to 2 kilohertz, and now we get the full peak of this resonance of the woofer. And by the way, you know this value also plays a major role for the TLS small parameter calculation and so on. Another parameter that plays a key role in GlideSweep testing in practice is the duration. Time is money, especially on a production line. So you want to keep the duration of a GlideSweep as short as possible. But what is the right value? That, of course, also depends again on the performance of the device under test, its behavior, and also the environmental condition. But as a rule of thumb, we can say the following. If we are covering, for instance, the typical audio band from 20 Hertz to 20 kilohertz, we would recommend a GlideSweep of 1.5 to 2 seconds duration, at least to start in the beginning of your evaluation process. If you have a higher start frequency, for instance 100 Hertz, we can already start with 800 milliseconds, so a shorter duration of the GlideSweep. And then after having accomplished the first measurement, having received the first test results, you can go to the next stage, and that is the optimization of this duration, saying you can now stepwise cut it down, minimize it with the trial and error approach. And that means you would repeat the measurement and compare the results with the initial status and the new shorter time. And as long as these results correlate, are identical, you can further go down and even speed up the test more and more, up to the point where the results start to deviate from the correct status up here. I show you here a fundamental graph that gives you an idea that, for instance, the GlideSweep duration strongly depends on the start frequency. The lower frequency of a GlideSweep, the start frequency, plays a key role for the overall duration. If we have a very low start frequency, 10 Hertz for instance, we definitely take more time to execute our GlideSweep, or the GlideSweep itself needs more time. Whereas with a higher start frequency, here we have 300 Hertz, we can reduce the GlideSweep duration tremendously, down to 0.1 second or 100 millisecond. Now let's talk a little bit about acoustic testing. As soon as you set up a test in an acoustic chamber, you will most probably face the effect from reflections. How do we deal with that? What can we do against that? Well, one approach is that you smoothen the acquired results. Smoothing means you apply a so-called gliding average. And in practice, this gliding average is typically calculated with a bandwidth of 1/3 octave. Well, this smoothing has an advantage. It is quite widespread. It's quite common. You even find it in specification sheets for loudspeaker testing, for instance. It has a drawback, however, as well, and that is that the results are not 100% true or accurate. And I want to show you why. Here we see the frequency response from before, from the woofer, and you see here it's quite nervous curve, jittery. You have some peaks up and down, and most probably these peaks come from reflections. It's not absolutely sure. But as soon as you apply the smoothing, when the curve looks like that, that is how you would present it in a specification sheet, for instance. The question stays about one or two of these peaks. Might they come from the speaker itself, or are they really reflections? That answer cannot be given if you apply the smoothing. So there is an uncertainty about this issue. However, there is also a second approach to compensate or to deal with these reflections, and that is by applying a time window. Now, let me explain what that means. Here we have a typical test setup for an acoustic device, for instance, a loudspeaker. Here is the device under test, the measuring microphone, and the whole thing is in a test gig. Now, when we execute our test, we transmit our GlideSweep. The direct sound will hit the microphone at first, but then we will also face some reflections from the walls. This is just one example. There are many reflections in this chamber. And they also hit the microphone and they add to the overall result. So when we look at that on a graph, up here we have the energy time graph. Down here we have the calculated frequency response. So up here you see that is the first incoming sound. This is the direct sound here. This red arrow represents this peak here, followed by more peaks which are definitely coming from these reflections. So by cutting off this part, this is the time axis here, cutting this part off, as you can see here this line tells me that everything behind this line is ignored. I all of a sudden get a very smooth and very nice frequency response. And, very important, this curve is absolutely correct. It's not like the smoothing I showed you on the slide before. This is the exact behavior of the device under test. Now, if I summarize, it means that time window application provides true results. However, there is also a disadvantage, because we are losing information here in the low frequency range. By cutting off this part of the signal here, the long-term reaction plus the reflections, of course, by cutting off this part, we lose the information for these lower frequencies. So that is the drawback, the compromise we have to take when we apply this method. Another example is now related to testing electronic devices. We have, for instance, electronic devices like this MP3 player you see here, which are able to replay sound, but they do not have an input jack or an input connector. So it is not possible to feed the test signal into the device for a test, but we just can replay it and analyze it. But how can we do that, or what do we need to consider? This is one example, and there's a very closely related example that is to testing transmission lines, which have a very long delay. So which means we send out the signal through the transmission line, and we do not know exactly when it will come back. But the analyzer must know when the test signal is coming in. So that is a challenge that has to be solved. It's very closely related to this first example. And the answer to both applications is that we apply a header to the GlideSweep. Here you see the fundamental setup of this test, and we are transmitting the GlideSweep, now adding a unique signal in front of the GlideSweep. So this is a combination of several sine waves, a unique combination, and the analyzer can detect this pattern, and as soon as it reads it, it knows now the GlideSweep will follow. So that allows the analyzer to synchronize to this incoming GlideSweep without exactly knowing when it will happen. In the next step, the analyzer can now calculate the measurement results out of the received GlideSweep, as here, for instance, the frequency response. Second application is closely related to the one I just showed you, and here we talk about latency measurement. Let's say we want to know the signal delay or the runtime of our signal on that transmission line. How do we do that? Here are just 3 examples of applications for latency measurement. For instance, a Bluetooth device, internet telephony line, or a signal processing device, compressor, or some other device for music effects, which also delays the incoming signal for a certain amount of time. Now, what is important to know, we can measure these delays up to 20 seconds, and apparently here we need a closed loop test setup. So which means the test instrument must know when the signal has been generated and when it arrives, and this way it can calculate the latency. I will actually show you a practical example of this application in the practical part of my webinar. A third application when we talk about electronic devices are items that include an automated gain control, be it an amplifier, mixing console, compressor. So these are devices where the output level not only depends on the input level, but it is also controlled by the device itself in order to avoid excessive high levels, for instance. So this automated gain control has the effect that it again takes a little bit of time of this device, the corresponding device, to settle to the new status. If the input signal changes, the device takes a little bit of time to settle to the new situation. Now, if we feed a GlideSweep in such a device, we don't want to measure the behavior during the setting time. We want to get a feedback of the status of the device when it is stable. And for that reason, we apply a so-called pre-tone to the GlideSweep. Pre-tone is a simple sine wave that has typically a frequency within the bandwidth of the GlideSweep, and it is just preceding the GlideSweep for a certain amount of time. You can select how long it will take. And this pre-tone allows the device to settle to this signal before the measurement itself starts. Now, here we are at the point of our practical presentation. I have a little bit a more complex setup this time. I explain that to you. We have the Flexus instrument connected to an amplifier. I will use the microphone of my headset now to transmit the output of that speaker to the internet, receive it back on my mobile phone, and from there I can feed it back into my Flexus analyzer. So having this closed loop, I can measure the latency of the signal, how long it takes from being sent out until it comes back, and of course also analyze the behavior of that transmission line. Let me switch over to the FXControl software, which you see here. So the first step would be to emulate this setup on this hardware and wiring worksheet, and that has the advantage that it makes it easier for you to understand the setup and to avoid any wrong connection or wrong parameterization of the software. Here I have added an active speaker. I connect it to my Flexus channel 1. I add a generic microphone. This is representing the microphone of my headset. And a generic I/O device. This is my mobile phone. The mobile phone receives the sound from the microphone via the internet and then feeds it back to the Flexus analyzer. Now in the next step, I will set up the test itself. And for that purpose, I need to control the output level of the FXControl. So I add this level panel, I unmute the Flexus, and I adjust the output level to the value that I need, in that case minus 20 dB volt. Second, I add the GlideSweep control panel. Here I can adjust the generator settings of my GlideSweep. For instance, the bandwidth, the start and stop frequency. So let's select 100 Hz to 10 kHz. Furthermore, I can cut down the duration of the GlideSweep, let's say to 500 milliseconds, half a second. And next, I add the analyzer GlideSweep panel. This is essential because I have here a setup where the analyzer does not know exactly when the GlideSweep will pop in, so I need the external synchronization. This means that the GlideSweep will automatically preceded by this header signal, the header that allows the analyzer to identify the incoming glide sweep. Last but not least, I want, of course, to see some results, measurement results. So I add glide sweep level channel 1, this graph here. And let's say we also want to see the smooth curve. So I go here to the worksheets, I select new calculation, and I add the smoothing calculation item. Of course, I have to tell the system the input data for the smoothing, and that is measurement glide sweep level channel 1. Okay, so by confirming, I receive this graph here on my worksheet that will show me the smooth curve of the frequency response. And last but not least, I also want to see the signal latency of my signal of channel 1. Now, to give you a more concrete idea of the setup, I have prepared a small webcam here, and I want to show you the setup in reality here as it is on my desk. You can see here the loudspeaker, the output of my signal. Then here I have my mobile phone. The mobile phone receives the signal via the internet, via Wi-Fi, and puts it out to the headset jack. So this blue cable leads the signal to the input of the Flexus analyzer. Now let us execute a test, and for that purpose I have to, for a second, take away my headset and put it in front of the loudspeaker. So you can see here the frequency response, the smooth frequency response, and down here we have the latency of our transmission line. So that is the time it takes from my speech to your device, or in this case to my mobile phone. So the delay that is happening right now during this presentation. By the way, if you wanted to add a pre-tone, which is not necessary in this case, you could do that here. I just mentioned that before. Here that would be the editable pre-tone for the test signal. Good. Let me get back to my slideshow and summarize what I have shown to you. First of all, very important, keep in mind, glide sweep analysis is the calculation of the impulse response. And from that impulse response data, we can derive a wide range of different measurement results. Very important that all frequencies within the bandwidth of the glide sweep, all frequencies are covered. So we can select, if we want to know the level at a specific frequency, we are absolutely free. There are no steps. It's a continuous or gliding sweep which provides all the information we want. And also important, glide sweep is a very fast test method, and another advantage, we can define the duration of the glide sweep in advance. Furthermore, I have shown you two methods to deal with acoustic effects like reflections. The first one was the smoothing, very common approach, and the second one would be the time window to eliminate these reflections. And the last topic was how to deal with electronic devices. We had the external glide sweep analysis, a very powerful tool for replay devices or very long transmission lines. We had the latency measurement, which I just showed you in my presentation. And if you have a device with automated gain control, you can apply a pre-tone for the compensation of this effect. Well, I'm at the end of my presentation. I would like to take the chance to thank you very much for your attention. I hope I was able to answer the questions you had. And of course, I would be very happy to welcome you again in one of our future webinars.